In the introduction, we see that today we stand at a critical juncture in our management of urban environments, where where rapid urbanization has created a lot of waste crisis across different cities in Uganda. So we are seeing that the traditional ways of managing waste, which is collection of waste at different points, has not been efficient enough, having the most critical challenge of segregation at the source. So what I mean is that we are trying to find a way of segregating waste that has been collected at the source where it's dumped originally. So uh, our proposal is a low-cost, energy-efficient smart bin that will help us get to segregate the different waste into the different categories, whether it's bio or non-biodegradable. So our problem statement, we have seen that most of the current solutions are kind of separated in that if a solution is found, it's focusing on maybe seeing if a dustbin or rubbish is at a certain level, whether full or empty. And other solution, they lack the waste segregation, where you find that the entire rubbish bin like accepts all kind of trash and puts it in the same place, which makes it hard to separate to these different categories. Then definitely uh, these current solutions are have a high cost and also have poor edge development deployment. So our main objective is to uh, find an find a way of creating a smart bin that can easily separate the bio from non-biodegradable at the source of disposal. Let me say dustbins in this case. At this particular point, once the trash is put in, it automatically gets to be segregated from biodegradable from non-biodegradable. So that's our main objective of the smart bin. Then the specific objectives were we want to develop a hardware prototype, a fully hardware functional prototype of this smart bin. Then we also have to develop a machine learning model that can easily recognize the different rubbish categories or trash categories and can easily separate the different categories there. So my colleagues will elaborate more on how this will be done, but these are some of our specific objectives. Then the third one is to implement sensor fusion for robustness. So in this case is more of adding sensors to detect moisture in degradable trash to help out the model to be more specific and more precise with its decisions. Then definitely the main goal is also the dustbin or the rubbish bin should be developed or built with minimal costs. So the significance of our research, the scope of our research. So we have the development of a standalone single dustbin prototype, as I've mentioned. Also, we have binary classification. So binary, it's either biodegradable or non-biodegradable. We are not breaking down further than that. And also low cost communication. So the significance, definitely we shall have reduced costs. We shall have improved waste segregation other than doing it the manual way at later stages, which is definitely hard and time consuming. Then we also have environmental benefits and as well as technical contribution. So let me have my colleague take it from the literature review.
Hello, my name is Sylvia and I'm going to take you through the literature review. So, in our key findings, we have four main key findings, which include the IoT bin monitoring, where there is mature and focusing on the field level of the rubbish and the trash, and also route optimization. Then sensor fusion, where there is promising for robustness but limited low cost evaluation by the sensors. Then the machine learning waste classification, where it is the active research area for variable datasets and deployment strategies are used to classify the waste. And the image-based data learning, where they use CNNs for classification and high lab accuracy, but poor real-world generalization. So, mm, the next slide, um, the literature review continued. We shall talk about the smart dustbins, which will be built using the ESP32s, the ultrasonic sensors, and we shall also incorporate SMS and cloud alerts to inform the necessary people of what needs to be done or what level of fill the trash bin is at, and so on. The next slide, the waste classification. Here I showed a table which classifies the different data sets and their different accuracies and times. We have the CNN based models, the TrashNet and the Taco data sets, and they show high lab accuracy and low field accuracy. The next slide talks about the relevant literature, where we have the machine learning models and sensor fusion. We have the mobile net and the efficient net, and also combining vision and sensors to use the sensors to determine what is being seen and where the trash should go. That is how we are combining the vision and the sensors. Then the improved robustness, where it is a robust system to cater for different types of trash and datasets and domain adaptation, ImageNet pre-training, where we shall train the models on different images to determine which ones are biodegradable and which ones are non-biodegradable. Then we shall use the Taco dataset, which comprises of very many images to come up with a clear description of which trash belongs in which set. And also localized data collection, where we can collect data from our everyday surroundings to determine what trash people around us mainly use. Thank you. My colleague will carry on from here.
Hello everyone, my name is Nabale Claire and I'm going to take you through the research gaps, and the first one is the integrated low-cost stack validated in field, and this one is mainly no integrated low-cost system, and most of the existing systems focus on only one part like the field level monitoring or cloud-based classification, and very few studies demonstrate a complete low-cost system that classifies waste, run on a edge hardware, and uses SMS communication with measured real operational cost. And the second one is the real-world label data sets. And here we lack the real-world label data sets, and for waste segregation, and available datasets lack mainly, sorry, available datasets like TACO mainly focus on litter, not waste inside bins, which reduces the model performance in real urban environments. And the third one is the energy latency aware models. And this one Many studies report accuracy but do not report energy consumption, battery life, inference latency on constrained hardware like ESP32. And these matrices are critical when deploying systems in the field. And the fourth one, we have the gap in sensor fusion for robustness, binary classification, and here most solutions rely on cameras only. However, combining vision and with simple sensors like moisture, gas can improve classification, especially in poor lighting or occluded conditions. Despite that, low-cost sensor fusion has not been widely evaluated in municipal settings. And the last one, we have a gap of the cost analysis at scale. And here there is limited research that analyzes the total cost of the ownership when systems are deployed at city scale, especially when SMSs are used instead of the continuous data connectivity. Next slide. Here we have the research methodology, and it has the four-phased approach. And the first one, we have the hardware design integration. And this one ensures that the system is built on a robust low-cost hardware foundation. And another one is machine learning model development and edge optimization. And this one involves collecting localized data, applying transfer learning, and optimizing lightweight model for edge processing, and also the sensor fusion implementation evaluation. And this one involves implementing and evaluating feature level and and late techniques for robustness. Mainly it's for validating classification and robustness yeah. And also the telemetry and cost analysis. And this one is all about analyzing the costs that we are going to use in the project. And here we have the hardware components and the data acquisition. And let me start with the hardware components, that the ESP32 controller, and this one is the brain of the project, of the system. And the reason as to why it is selected, it's because of its low cost, and the lightweight system can easily run on it, and also collects data from sensors and run machine learning models and control communication. And also ultrasonic field level sensor is for sensing the level of the bin. Then for the low cost camera module for image acquisition, which for the WES, which is used for machine learning models, and also the auxiliary sensors for moisture, gases. These ones are for non-visual classification, and the GSM, is for sending SMS alerts when the bin is full, and also the battery and solar panel is for providing energy power to the system. And the data acquisition strategy, we decided to try for the secondary data, we decided the pre-trained mobile net v2 from ImageNet Taco dataset, because we used the pre-trained mobile net v2 from the ImageNet Taco dataset and the primary localized data images from Uganda bins under various conditions.
Hello, my name is Singwe Eric Hannington. and I will be concluding with evaluation metrics. And in the evaluation metrics, we shall be talking about the classification metrics, performance metrics, and I'll conclude with the total cost of ownership. Under the classification metrics, here we're talking about the ability to correctly identify waste that is evaluated using accuracy, precision, recall, and F1 score. So these metrics are going to compare three different setups. That is a vision only, feature fusion, and the late fusion models that so that it can find the most reliable method. Under the performance metrics, we're going to ensure the system is practical for field use and it is tested for latency, as my former colleague has mentioned. Latency, we're going to be seeing how fast it makes a decision in milliseconds. Then also, we're going to be dealing with energy consumption, which will be measured in watts or joules per inference on the ESP232 hardware, which is among the hardware that we're going to be deploying. Then the total cost of ownership, we're going to provide a long-term financial analysis for scaling the project. The project will cost for 100 to 500 bins over 3 years, specifically comparing the affordability of SMS-based telemetry against the conventional data heavy communication methods. So that will be our total cost of ownership. And the conclusion, expected outcomes, we have a functional low cost prototype that offers a scalable solution for improved urban waste segregation. And our estimated budget, which is on the next slide, for a single prototype will be approximately 360 US dollars. And with that, uh, that concludes our presentation for our smart dustbin. Thank you.